let's look at an example that involves tangent planes. So I'll share my screen. For this example, we have compute a set of parametric equations for the tangent line to the curve of intersection of the surfaces at the given point. And we're given the upper nap of the double cone, that is z equals the square root of x squared plus y squared. And the other surface is a plane, 2x minus 3y plus 8z equals 34. And we want to construct the tangent line at the following point, 3, 4, 5, and I've just labeled it P. Notice this is a point that satisfies both surfaces. So we don't have to compute the actual curve of intersection. We simply can compute the normals to each of these surfaces at this point, and then we can find the direction of the tangent line by computing the vector product. So this is more like an example that we had in the previous chapter, chapter 11, on vector analysis, now involving some more calculus, just like we saw with vector curve theory. So let's go ahead and do that. Let's get our implicit equations. That is, we can use uppercase F for the cone, and this will give us x squared plus y squared to the 1/2 minus z. And then for the plane, we can use g equals 2x minus 3y plus 8z minus 34. And of course, both of these equal 0, and that gives us an implicit setup, an implicit equation. So if you want, you can just go ahead and include this. Now we can take gradients to get the normals to the surfaces. So fx will be 1/2 x squared plus y squared to the negative 1/2, and then using the chain rule of 2x. And we can go ahead and simplify here. The 2's obviously will absorb. And we're left with the x in the numerator. And of course, you can remove the radical to the denominator. Now we get a symmetric calculation for the y partial, 1/2 x squared plus y squared. Well, I'm doing it, but you could probably just go ahead and write it down, 2y. And again, the 2's absorb. And we're left with y divided by the square root of x squared plus y squared. And then, of course, the z partial is very straightforward. We just have -1. Now, of course, over here, we have the normal built in. We don't even have to do the partials, but of course, it's consistent. So we have gx is just 2, gy is just -3, and gz is +8. And now, well, we can go ahead and write this down. The gradient of g evaluated at 3, 4, 5 doesn't change, it's constant. We just have the vector 2, -3, 8. So we go ahead and write that down. And of course, we don't have any nice common factors there, so we'll leave that as it is. And then, of course, now the gradient of f at 3, 4, 5, nice Pythagorean triple. Okay, so we've got the square root of x squared plus y squared. In both cases, that's 5, square root of 25. So we get 3 over 5 and 4 over 5 And then, of course, the -1, which just comes along for free. Now, notice we do have the 5 in the denominator, which can be factored just to neaten up the arithmetic. So we get 1/5, 3, 4, and then, of course, to compensate a -5 here. Now, we can drag the 1/5 through the calculation, but when we take a direction for the tangent, we can omit that. We don't have to have any constant multiples. We still preserve the quality of the vector without them. So now to get a direction that will be useful to us, we look at the vector product. So we're going to take the gradient of f, and I'll just go ahead and leave out the points where we've evaluated it for clarity and just to have less to write. By context, we know we're dealing with these vectors. So we've got the 1/5, 3, 4, -5 vector product with 2, -3, 8. So again, as you see with the theory of the tangent planes, we keep reusing what we have. That there's such a elegant synthesis between the ideas from Cal 1 that we transferred to Calculus 3 that make our computations doable. So now we could just use our formula for the vector product, and I'll just remind you of that. We have what? 2, 3 minus 3, 2, and then 3, 1 minus 1, 3, and 1, 2 minus 2, 1. But just looking at the subscripts or the components of the vectors, that's a very simple way to do it. And that's how I derive theory for the vector product to make it reasonable. So now we have 1/5. And then 2, 3, so that gives us a 20, 2, 3, 4 times 8, that gives us a 32. Then minus 3, 2, well, we've got a positive 15 because of the 2 negatives, so we have minus 15. Now 3, 1, a -10, minus, and then 1, 3. So we get what, in this case, a 24. Now 1, 2, 1, 2 is a -9, minus 2, 1. So again, 2, 1, we have an 8, so subtract 8. Hopefully, well, you can see we have some good numbers. It's not going to be unfortunate. Lots of times with vectors, we get some really unfortunate numbers. But now, of course, if we subtract the 5 from the 12, we get a 7, and then that leaves us with a 1 from 2. So that gives us a 17. And then adding this, we get a -34, which is a multiple of 17. And then, of course, this gives us a -17. So this is what I was talking about before. We can now refine this by just extracting the 17. So we have 17 over 5, 1, -2, and a -1. So at this point, what we can do is the scalar factor, there's no problem with it, but it's basically in the way, and it's not going to take any information away from this particular vector in terms of direction. So at this point, and I'll write this in red, we will take the direction vector, and we often use direction for lines as the Greek nu. It looks like the V. I use it for V and velocity because it's easy to write. So we'll have 1, -2, -1. So that gives us the direction of the line. And now the parametric equations are very simple. We've got this direction, and then, of course, the point here, which I've covered up, P, 3, 4, 5. So now This implies that we have parametric equations. X will be t, if we just use t as a parameter, plus 3. Y will be negative 2t plus 4. And then z will be negative t plus a 5. So what we can see with the calculation here is that as we review, we are not tasked with computing the actual curve of intersection. We're simply interested in some calculus at a particular point. So the technique of utilizing the gradient to compute surface normals and then the vector cross product to actually compute a mutually orthogonal vector, which will align with the direction of the tangent line. And so therefore, we can simply box this, and we have a set of parametric equations, which will complete the problem, and we are done.